Here is another classical mechanics problem. And we're going to solve this using work energy principle and momentum, but we'll again come back to this when we're doing Lagrangian mechanics. So I want you to be able to do it first. So the problem is a wedge right here and a block on it. There's no friction, but the wedge is movable. Movable wedge. It's the classic movable wedge problem. So we have a mass m2, the angle theta doesn't really matter. The block m1 starts at a height h above the ground. So as this slides down, that's going to go that way. And I'll show you about the normal force. We talked about this before. Calculate the normal force for a non-movable wedge. But I just want to show you one more thing in a second. So if we want to use the work energy principle here, we have to choose our system. So I'm going to choose my system. So I'm going to say I have the system of let's say m1 plus m2 plus the Earth. And why do we have to include the Earth in our system? If you want to have gravitational potential energy, it's not associated with an object, it's associated with an interaction. So in order to have a gravitational potential energy, I have to have the interaction between m1 and the Earth. So technically it should be in there. Okay? Otherwise you can get yourself into a lot of problems. So with that, I can say, well, what's the work done on my system of all these three things? Well, gravity doesn't do work because it's part of the system. We do have these normal forces which do work in this case. Normal force does do work. However, we have two normal forces, right? I have a normal force that the wedge pushes on the block and the block pushes back with the same amount. So it's an internal force. No work done. Now there's a normal force between the bottom surface of the wedge and the wedge, but that's this way, and the wedge is only going to move horizontal, so it doesn't do any work. And there's no friction, so we're all set. So I can say 0 is going to be the change in kinetic energy for 1, plus a change in kinetic energy for 2, plus a change in gravitational potential energy for 1. Now, object 2 has no change in potential because its height doesn't change. Remember, in a constant gravitational field, the potential is mgy. U is mgy, and we only care about the change, so we can pick where that y value is equal to 0. So I'm going to pick the location of the box. I'm going to pick, it has a y value, and whatever that value is its potential. Let's just go ahead and write our equation. So I have 0, 1/2 m v1 final squared. I'm just going to call that v1 squared. I know that's dumb. Minus 0, right? Because that's the initial kinetic energy. If I release it from rest, is 0. So that's why I can say that's V1. It's block 1 final. Okay. Plus 1/2, oh, that's M1. M2 V2 squared minus 0. Again, it started from rest. And then I have the final potential energy plus 0, right? Because this block's going to end up down here where the y value is 0. Minus m1 gh, which is the initial position of the block up here. So I have this nice equation. Let's just write it a little bit simpler. 0, 1/2. I'm going to write, I'm going to multiply both sides by 2 because that's what I want to do. 1/2, m1 v1 squared plus m2 v2 squared minus 2 m1 gh. So that's one equation. Now, but I don't know v1, I don't know v2. I don't know either of those. So I need another equation. And we can get that other equation from the momentum principle. So if we look over here in the x direction, I can say F net x is delta px delta t. So at the end of this, the block's going to be down here like this. We're going to have the wedge moving with the velocity this way, v2, and then we're going to have the block over here moving with the velocity that way, v1. So they're both going to be moving in the x direction at the end, and that is kind of a trick, right? Because we don't get the motion as it moves down right away, because you know why, right? Because this doesn't give us direction. And then the motion of this is a little bit more complicated, but we can get it later when we come back to this. We will. Okay. So if that's the case, the net force on this in the x direction is 0, right? Because there's no forces pushing on these blocks. So the change momentum of the whole thing has to be 0. So that means the momentum before, which is 0, has to be the momentum at the end in the x direction. So I can write this as m1 v1 equals m2 v2. So that's from conservation of momentum. But it gives us a second relationship between the two velocities. So I actually have two equations, two unknowns. I just need to solve these. So let's take this and solve it for v1. v1 is m2 over m1 v2, and plug it in up here. I'm going to move that to the other side. 2 m1gh equals m1. Now for v1 squared, I'm going to square this. So I get m2 squared over m1 squared v2 squared. And then plus m2 v2 squared. Now I have an equation with just v2. That's my only thing I don't know. Okay, so this actually right here, I have an m1 and an m1 squared, so I can magically erase that like that. And I can factor out the v2. So v2 squared is m2 squared over m1 plus m2. And then I can divide both sides by that. I get, making sure I'm not running out of room, v2 squared is 2 m1gh over m2 squared over m1 plus m2. And then I can take the square root of both sides. And that's the velocity of the wedge. Now what about the velocity of the block at the end? Well, I can just multiply by m2 over m1. So I can say v1 is going to be m2 over m1 square root of 2 m1gh over m2 squared over m1 plus m2. And you could simplify the sum if you want, but I'm fine with it. Let's write this up here because I want to have a little bit more room to play with it. Because we want to check our answer. I'm going to do a numerical calculation. You know that, right? You knew that because I already had this idea of using a block on a plane. I did a block on a plane where the plane did not move, so now I'm going to do with it moving. So let me first of all talk about the work done by the normal force, because the work done by the normal force on one block is not 0. So let's just go up here. Here's my block, and here's my wedge and my block. So as this slides down, the wedge is going to move this way, the block's going to move that way. So the path is going to be down like that. Not straight down, it's not going to go in a straight line. But the normal force is that way. So as I do the work as the integral from 1 to 2 of n dot dr, well, this path and that are not perpendicular, so it does do work. And in fact, it's going to do negative work, right? Because the angle is greater than 180 degrees. So if the normal force does negative work on that block, then it's going to end up, well, it's still going to speed up, because gravity does positive work on it, you could think of it. But at the end, it's going to be going slower than it would otherwise. However, if I take that same force right here and apply it to the wedge, it's going to be like that. It's going to move along that same path, and it's going to do positive work, so it's going to speed the wedge up. So if I had the unmovable wedge, the block would move down this way, and there would be no work. The work done by the normal force would be 0. But the other way, if you want to break it into 2 blocks, you can see that the work done by the normal force is not 0. And that was one of the things I said before. I just wanted to show you that. Okay, but here we have v2. I want to put it up here because it's too low. v2 is the square root of 2 m1 gh over m2 squared over m1 plus m1. So let's check special cases and stuff. Let's number one check the units. Okay. So here I have mass over mass, so the mass cancels. So that's meters per second squared times meters. So I get meters squared per second squared. I take the square root. It does have units of meters per second. Okay. Now we have 3 special cases. What if m1 equals m2? If they're the same mass, then at the end, according to conserve momentum, they have to have the same velocities. So if I put in m1 is m2, then this is going to be m over m squared over m, which is just m, plus m, which is 2m, and that cancels right there, so I get 2gh. And then if I come over here, if for v1, the masses also cancel, these cancel, and I get the exact same thing. Okay, so they're the same thing, which is half of the speed of an object that fell from that same height. Okay, so that's check. What if m1 is much less than m2? So this is a very, very massive wedge. In that case, the wedge will basically not move. And if the wedge does not move, this should have a velocity of square root of 2gh. So if I come back up here, I kind of messed up I touched it. You shouldn't touch things. Don't touch stuff. That's what they tell you, don't touch it. Okay, so if m2 is very large, then this term on the bottom is just m2, okay? Right? Oh, that's v2. Ha ha ha. So v2 is going to be have no velocity, right? Because we're dividing by a very large number. Down here, I have, again, this looks like no velocity, but I'm multiplying by some. So I'm going to need to multiply this into the whole thing to see that I get, I'm not going to do it, but it does work. Trust me, I don't want to do that right now. Okay, so let's check. You can check that. That's a homework. I'll give you homework. What if m1 is much greater than m2? Okay, in that case, the wedge has no mass, and this block's just going to fall straight down, right? And the wedge is going to go flying off to the side. So over here, oh, that one is going to be infinite. Over here, oh, again, it's not going to be super easy to show. You need to multiply it in, but again, homework problem for you. Because I want to do the numerical calculation. I want to model this numerically. So we can do that with the same trick I had before. So that's an important formula that we can use to check, but I'll put it way over here. Let's just do v1. v1 is m2 over m1 square root of 2 m1gh over m2 squared over m1 plus m2. Okay, so I need that. Great. So how can we model this? Here's what we're going to do. And there's some tricks here. So I want to if I can calculate explicitly that normal force, and I can calculate explicitly the gravitational force on this mass. So I can say m1g, and I can calculate n. If I can do that, then I can just say F net is n plus m1g, and that's equal to the change in momentum with respect to time. And with that, I can break this into short time intervals. I can calculate the change in momentum, assuming this is constant, and then I can use that to find the change in position. I've done that a billion times. I'm not going to go through all the details. I'll show you in a little bit, though. Okay, so we'll calculate the force, update the momentum, P2, P1 plus F net times delta t. Update the position, let's just call it R2, R1 plus P2 over M1 delta t. So that's your normal numerical model. Now, but the question is, how do you calculate that normal force? So if I let the mass go below the plane, then I can make it act like a spring to push back that way. So the normal force, I'm going to say, is going to be equal to, if it's below there, it's going to be equal to negative k, and this, we'll call this distance it travels there s n hat. So n hat's a vector in the direction, unit vector in the direction of n. So that's if it's below there, okay? And k is a spring constant, and s is that amount. So I just need to say, is it in the wedge or not? If it's not in the wedge, then n is equal to 0. If it is, it's equal to that. So how do we do that? How do we calculate the distance over there? Well, what I'm going to do is I'm going to make a wedge. Let's draw like here. I'm going to use just a block like that. And then I have my block right here. In Python, we know the center of that wedge. I'm going to find a point up here, and I'm going to call this the vector r, r. I don't even know why I called it RR. So RR is a vector from the end point to the middle of the block. And then wherever that block is, I can find this distance S0. It's going to be the initial height above there. It's going to be right on the plane, but it's going to the center of the block, and I got the center of that. All that stuff's messed. Okay. So I can calculate S in general. S is going to be RR dot n hat. Right? So if I take the dot product, I get the component in that direction of n hat. So I actually get this distance right there. So if that distance is negative, then it's, well, then S, I want to say, is S minus S0, is that distance from the block. And if that's negative, then I make a spring force. If there's not, there's no spring force. And then once I calculate the normal force on this block, I can model its motion, and I can apply that normal force to this block over here. Now, I will have to apply just the x component of that normal force because I don't want that block to move up or down. I know it's a lot, but we're going to do it anyway. Okay, so I already started because I had trouble setting things up. So here is my start right there. Okay, so what I did was I made the ground, I made the wedge, which is another block, I made the mast. I just manipulated them around until I could get them to work. And I also made this thing called wedge.p1. That is the top point of the wedge, where I measure that RR from. Okay, let me run this so you can see what it looks like, because it actually does look pretty cool. And then I'll tell you. So there's my wedge, there's my block, and it's on this ground. Okay. So just so you know, the angle theta, it's just theta. That's the length of the wedge. And then what you can do is you can make a block, and it gives you your position at the center of the block. And then what I can do is to rotate that whole object with the rotate function. So the rotate function, you tell it how much to rotate. That's the angle. The axis about which to rotate. In this case, I want the z axis. And then the origin about what you want to rotate. So I rotated about the corner so that I had it down flat, and then I rotated it up. So now that's done. And then the point P1, it's the center of the wedge plus this vector based on the angle, right? So that's pretty easy. And then n hat is a unit vector in the direction of n, which is based on the angle theta too. So that's pretty simple to see. You can play around with that. Okay, so we need some more constants here, so let's just get to it. Is this big enough? I feel like it should be a little bit bigger. You know I like it big. Okay, g equals vector 0, negative 9.8, 0. I need k. Let's say k is 1,000. That's my spring constant. I need the two masses. I'm going to start off with the two masses the same. And I'm going to call them m1 of 0.2, m2 of 0.2. I could assign these as a property of an object, but I want to be able to change it easy, and I just didn't want to do that. Now I need to calculate that initial S0, right? How far above the wedge does it start? I'm going to say it's at 0, right? I need to know what that value is. So RR is going to be the vector from the wedge to the box, which I call mass. Mass.pos minus wedge.p1. Right? So you can assign new properties to an object. If I have a wedge, I can assign this vector called P1. Python doesn't care. It's like you do whatever you want. You can assign stuff to that. So S0 is going to be the dot product of RR and n hat. Right? So that's fine. And let's just print that and see if it works, because you never know if things are going to work or not. It shouldn't be 0. Okay, so that seems reasonable. Okay. What else do I need? I need to assign the initial momentums of the two objects. So mass.p, the momentum is going to be 0. Wedge.p, vector 0, 0, 0. I need my time. I need my time step. And you do want this to be smaller than normal because when we're dealing with things going in and below that thing, we want to be able to calculate that very quickly. Yeah. Let's see. I think that's it. Okay. So let's make a loop. I want to let it run as long as the block is greater than 0. So I'm going to say while mass.pos.y is greater than 0, do the following. I'm going to run it slow motion, right? So it's a 1/1000th time step, but I'm going to run it in 200 frames per second just so we can see what's going on. So the first thing I'm going to do is, what did I do before? I need to calculate that RR. Right? I'm going to need that. I'm going to calculate S dot RR in hat. Okay. Now I'm going to, let's just see, I'm going to do this. N equals vector 0, 0, 0. So if this is not true, then N is, every time I get back to loop, I'm going to set N equal to 0. So if S minus S0 is less than 0, then there's a spring, right? Oh, actually, I did it this way. I just did this as minus S0. If S is less than 0, then there is a normal force, and I need to calculate that. So N is going to be negative K times the magnitude of S times, no, S is a scalar, S times N hat. Yep. Now I can calculate the force on F1, on mass 1. So F1 is going to be N, whatever that force is, plus M1 times G. I'm going to not calculate the forces on the wedge yet. I'm just going to model the motion of the block. I did this before, but I want to make sure things are working. Now I can update the momentum. Mass.P equals mass.P plus F1 times dt. Update the position. Mass.POS, mass.POS plus mass.P times dt divided by M1. And then update time. T equals T plus dt. So that should work. Let's just see what happens. You never know. Oh, something happened. What the heck happened? S is the dot product of RR in hat minus S0 in if it's less than or equal to 0. N is negative KS in hat. P maybe that was it. Is that it? That couldn't be it. What the heck? Why is it doing that? What if I change that to 100? I think I got my N hat wrong, maybe. N hat, sine theta, cosine theta. That's right. Huh. S0, dot product, RR in hat. Oh, I see what I did. I got this backwards. I did that on purpose just so you can see what happens when you make a mistake. Okay, and let's put this back to K as 1,000, and let's run it again. Awesome. Okay, and so it goes through the floor because I didn't have any check with that. That's fine. Okay, now I want to also move the wedge. So to do that, I have the wedge's momentum. I need to calculate the force on the wedge. And it's going to be the same as N, right? So let's just call this F2. I'm not going to give a gravitational force on it because that's balanced by the gravitational force of the ground. It's just going to be the vector negative N dot x 0, 0. So just the x component of that vector N, but in the negative x direction. Now I can update the momentum. Wedge dot P equals wedge dot P plus F2 times dt, and then I can update its position. Wedge dot POS, wedge dot POS plus wedge dot p times et divided by m2. Now, I do need to update that position, that wedge 1 dot p1, right, up here. So let's just copy the code where I had that up there. I'm just going to do it again. I need to recalculate that because it moved. Okay. I think that should work. Okay, that looks good. I like it. Let's just print the velocities and then print the theoretical velocities. That's what I want to do. And let's just do, I have a V1. So let's just print V1. I'll print both the velocities experimentally. I'm just going to print the magnitude of the velocity. So that velocity is moving down, right? But I'm going to calculate, I assume it would hit the flat plane and level off. So I'm going to print the magnitude of it. So print V1 equals, it's going to be p squared over 2m. So mass dot p squared divided by 2 times m1. And that's in meters per second. And then print, this is the theoretical, V2, this is the experimental, mag wedge dot p squared divided by 2 times m2 and meters per second. And now they should be the same, right? Because they're the same mass. Let's just run that and then we'll calculate the theoretical. They're not the same. Huh. Maybe I just have to do the x component. Yeah, that's true, because so I just want the x component of this velocity, because there's going to be a change in the velocity that way. So p dot x squared, and I can just take off this. Okay, check. Okay, now let's print the theoretical for V1. So let's calculate that as V1 theoretical. It's going to be, I'm looking at my equation right here, m2 over m1, m2 divided by m1 times square root of, oh, I don't have h. So let's say h is mass.pos.y, I think. 2 times mag g, g was my vector, so I have to take the magnitude of it. 2gh m1 times m1 times 2gh divided by m2 squared divided by m1 plus m2. And let's print that. Okay. Huh. M1, M2 over M1 times 2 M1GH. The only thing I can think of is my H is wrong. Divided by M2 squared over plus M, yeah. Okay, well, I'm going to leave that as homework for you to figure out. I think it's all working fine. We could do one more thing. I could increase the mass right here to something like 2, and we can see if it does stay stationary. If that's the case, I'm pretty confident that everything's fine. Yeah, okay, I think it's good. So I'll give you a link to this code down below. You can fix it, find out what the problem is. But remember, we're doing this because we're going to redo this problem later, and I want you to have a solution to this problem now so that we can compare later. But that's that. I'll talk to you guys later.